This is the second lecture in section 1.1, and in this lecture we're going to focus on the energy associated with electromagnetic radiation. So by the end of the lecture you should be able to calculate the energy of a photon and the energy for a mole of atoms releasing photons. You should also be able to state the relationship between wavelength and energy. When trying to work out the energy of electromagnetic radiation, it is useful to consider electromagnetic radiation as being particles. Now, these particles are known as photons, and we can work out the energy associated with a photon of a given frequency or wavelength. So, the energy of a single photon is given by the equation E equals hf. Now, H refers to something known as Planck's constant. And it's got a value of 6.63 times 10 to the minus 34. Now, you don't need to remember that number as it's in your data booklet, and you'll find it on the back page of your data booklet. Okay. F, of course, refers to the frequency of the radiation. Now, sometimes we're not told the frequency, sometimes told the wavelength. Now, we know that C equals F lambda, so we can replace F by C over lambda, and so sometimes we also use the equation E equals hc over lambda, okay, to work out the energy of a photon. However, more often in chemistry we have to work out the energy associated with 1 mole of photons. Now remember, mole is just a very large number, 6.02 times 10 to 23, known as Avogadro's number, and that's what the L here stands for. So the L is Avogadro's number. The L there is Avogadro's number, 6.02 times 10 to 23, which is also given in the back page of your data booklet. H is Planck's constant, and F is the frequency. Once again, sometimes we're given the wavelength instead of the frequency, so another way of writing that equation is E equals LHC over lambda, and using that we can work out energy associated with 1 mole of photons. So this equation, E equals LHF, is the equation that you are given in the data booklet with all the other equations. E equals LHF. In the vast majority of questions, however, what you're asked to do is to calculate the energy in kilojoules per mole. So this will give us the energy in joules per mole, not kilojoules per mole. So in order to convert it into kilojoules per mole, we use the equation LHF divided by 1000. Okay, so divided by 1000 changes it from joules to kilojoules. Or again, if we replace the F with C over lambda, the equation becomes E equals LHC over 1000 lambda. And it's in this form that you'll most often use this equation. Okay. So this is a form you most commonly use. Not always, occasionally you might be given the frequency instead of the wavelength. Sometimes you might be just asked for the energy of a photon instead of a mole of photons. So if it's just 1 photon, you lose the L. Okay. But this is the version you'll use most often. It's not in the data booklet. This one is in the data booklet. So you have to make sure you can convert that into that. So just replace the F with C over lambda and you divide by 1000 to change from joules per mole to kilojoules per mole. Okay, so let's look at an example. When put in a Bunsen flame, strontium gives out red light with a wavelength of 670.7 nanometers. Calculate the energy in kilojoules per mole associated with this wavelength. So we're going to use the equation E equals LHC over 1000 lambda. Okay. So L is Avogadro's number, 6.02 times 10 to 23. H is Planck's constant. If you can't remember it, look up your data booklet, back page, and you'll find it says it's 6.63 times 10 to minus 34 multiplied by C, speed of light, 3 times 10 to the 8. Okay. I really love the huge differences in scale between these numbers. Planck's constant's tiny, 10 to minus 34. Avogadro's number's huge, 10 to 23. So divided by 1000 times lambda, where lambda is the wavelength, which is 670.7 nanometers, but we have to work in meters because the speed of light is in meters per second. So 670.7 times 10 to minus 9. Okay. And that works out at 178.5 kilojoules per mole. When giving your answer, please try and avoid using too many significant figures. Normally I'd use 3, in this case I've used 4. If you start using 6 or more significant figures, you will lose marks. Okay, here's another example. When electricity is passed through a sodium vapor lamp, orange light with a wavelength of 589 nanometers is produced. Okay, so given the wavelength of 589 nanometers, calculate the energy in kilojoules per mole associated with this wavelength. So pause the tape, try to do this question yourself, and then look at the answers that I'll provide. So pause the tape, try it yourself. Okay, so hopefully by now, given the wavelength, you can work out the energy associated with a type of radiation. So let's look at the electromagnetic spectrum again. And consider the energy of these different types of radiation. Here we've got very long wavelength, and of course, if you consider how you work out the energy, LHC over 1000 lambda. If the wavelength is big, the energy will be small. If the wavelength is small, the energy will be big. So the radio waves with a big wavelengths will have little energy, whereas the gamma rays with a small wavelengths will have a lot of energy. So we find that the increasing energy as you go from the long wavelength to the small wavelength. And that kind of makes sense. Let's consider this situation where you've got two waves let's assume they're electromagnetic radiation. One's got a short wavelength, one's got a long wavelength. If you imagine you're sitting on a little boat on both these waves, you can imagine the short wavelength is going to do you a lot more damage. So they've got a lot more energy, you'll be bouncing up and down a lot. Whereas this one, it's slightly more gentle motion. So short wavelengths have higher energy. Okay. So So we've got long wavelength here, low energy, small wavelength here, high energy. And if we just look at the visual spectra for a second, remember the blue end is about 400 nanometers in wavelength, the red is about 700 nanometers. So it's imperative that you remember that the smaller wavelength has got the higher energy. So the blue is more energetic than the red at 700 nanometers. You know, so easy just to think, oh, the higher wavelength, that's higher energy. No, it's the other way around. And if you look at the waves down here, on the whole, they're not particularly dangerous. We've got radio waves all around us all the time. Don't do us any damage. Visible light doesn't do any damage. But once you get up here, ultraviolet rays are bad for us. X-rays are bad for us. Gamma rays are bad for us. These things up here cause a lot of damage because they're high energy. These things down here aren't nearly as dangerous. So that's the energy associated with electromagnetic radiation and the electromagnetic spectrum. So by now you should be able to calculate the energy of a photon and the energy for a mole of atoms releasing photons. And you should also be able to state the relationship between wavelength and energy.